Recording is rolling. It is Tuesday, October 8th. We're on Friday bill schedule today, so we have about 37 minutes to work with. Of course, they're letting us go early for this hurricane that's barreling our way. Gotta prep for that. I'm gonna walk you guys through this rotational kinematic motion lab today. You guys have turntables on your desk. You guys have a protractor. You guys got rulers. You guys have some kind of mass slug. I'm gonna use these. You guys probably have something about like this. I'm gonna call this a slug. I have a few Roosevelts here. I'm gonna be using myself. We're not gonna be able to finish the whole thing today, but I'll get you guys as far as we can, and then probably have to finish this on Friday. So because this hurricane is headed our way, a bunch of dates have been changed. So PSAT, do you guys see what day the PSAT is now? Right, so Thursday the 17th. If you're in 10th grade, you're probably taking it. You might be taking it otherwise, but guys, whether you're taking it or not, it is relevant to this class because, guys, is this classroom being used for testing? Yes, it is. Actually, it's extended testing, so all day. So is anybody going to show up to this classroom on this day? Not unless you're taking it in here, which is unlikely. So where are you guys going to relocate instead? Yeah, media center. There you go. Library, media center, and I'll be there with you guys. So do that. ASVABs on Tuesday the 22nd. I don't know yet if that's going to affect us or not, but here, I'll say when I get closer. Picture retakes are now on Friday the 25th. Right. Oh, this last note here. Here, I'll read this anyway. This was really for my AP students, but some of you guys might be taking an AP exam. Is AP's been trying to move exams from paper and pencil, which has been in the past, to digital. I think they've got a program called Blue Book or something. And 12 of the exams, including AP Physics, they are going to embed this Desmos calculator. Now, this is something, maybe, have you guys used this calculator, Desmos? It's a graphing calculator. You can Google it. It's on the internet. Go to Google, type Desmos. It'll pop up probably at first link. And I'm really recommending, especially to my AP students, and you might be an AP student, some class, that maybe you use that calculator a bit so you can familiarize yourself, because every calculator has a little bit different notation, or the buttons are different places, or different functions, or maybe you have to close parentheses in a special way or something. So yeah, familiarize yourself with that calculator so you know what's going on there. All right, so you guys good with the setup? You guys ready to do this lab about? Right. So here, do a little bit of review with you guys, because yesterday I introduced a bunch of new concepts. So I'm going to go through this a bit fast, give you guys a quick review. Up until before yesterday, we'd only ever talked about motion in straight lines, either forward and backward, up and down. Right? Now, I know we also had projectiles, but even that you could break down into just horizontal and vertical motion and treat those independently of each other. Right? Now we're going to get into this turntable type motion. What if something's like spinning? Right? Spinning. I got this turntable here. What if something's like rotating? Okay. So now we're going to say how far is something turned, right? And here, do you guys remember, guys, angular displacement? That's how far something turned. Here's Greek letter theta to represent that. I can think of at least 3 different ways to measure how far is something turned. Guys, what's one way to measure how far is something turned? Huh? Degrees? Degrees? Yep. Yeah. And that's what you have the protractor for on your desk. You're going to use this protractor later today to measure degrees. Right? What's another way to measure how far something turned? Radians, and that's why I got on this poster, right? And there's also like revolutions or rotations, right? Like Earth makes 1 rotation every 24 hours, something like that, right? Now, why do I really care about radians to measure how far something's turned? Why is that like the best way to measure angular displacement? What's special about radians? Okay. Guys, here's what's special about radians. If I flip ahead a few posters to these kinematic equations, you guys remember kinematic equations, right? If you plug in, like see this angle theta right here, could this ever be in degrees or revolutions for that matter? No, it has to be in radians, and this has to be in radians, and this omega has to be in radians per second, and this alpha has to be in radians per second squared. If you try plug in and chug in degrees, it's going to blow up. It's going to make no sense, give you nonsensical answers. Same thing for here. If you want to convert back and forth between linear and angular type motion, this has to be radians per second squared, has to be, right? If you pay real close attention, any time in the past that you've ever plugged in some angle in degrees, it has always, in a calculation, been inside a trigonometry function, sine, cosine, or tangent. It's always been, right? But if you want to directly multiply an angle, it has to be in radians, right? There's also angular velocity, radians per second, angular acceleration, radians per second squared. Here, this is a similar type poster, but it says, well, what are the rotational analogs to this linear motion? Here's linear, here's rotational. So time in seconds is still time in seconds. You guys got a stopwatch on your desk, be using this later. Right? Instead of saying how far in meters, now it's saying how far something turned, turntable turn, and yeah, we're going to focus on radians as the unit. Right? How fast is a car going in miles per hour, meters per second? No, now I want to know how fast is something spinning. So here's omega for angular velocity, right? Now I'm saying radians per second. Have you guys ever heard RPM? Guys, what does RPM stand for? Revolutions per minute. Hey, is that a type of this right here, angular velocity? It is, right? Now, of course, we're not going to use that in our calculations, but that's what it is. Right? It is a type of angular velocity, how fast something's spinning. Right? Could that turntable be speeding up or slowing down spinning? That's angular acceleration, kind of like a car speeding up or braking to a stop, but now it's going to be a turntable. Right? And then the bottom half of this table, don't worry about until December, okay? Unless you want to look at it, but I'm not going to talk about it until December. Right. Now let's translate back and forth between angular motion, which is these three characters, and linear motion. Maybe I'll call this like tangential velocity, for example, for this one, or tangential acceleration. Right. So here, I'll show you. I know this is my my cartoon version of it, but let's do the real live version right here. Right. So I got 3 Roosevelts of it. I got a question for you guys. This thing is spinning. Guys, these 3 Roosevelts. Which one of these 3 Roosevelts has the fastest angular velocity? Like turns per time. Or is that a trick question? All the same. Guys, they're all doing the same turns per time. Are they all doing the same revolutions per minute? Yep. Are they all doing the same radians per second? Yep. That's angular velocity. They're all the same. They're all doing the same turns per time. Right? Now, guys, what about a different question? Suppose I start pointing radar guns at them. Or what if I have a speed gate and I go going through the speed gate? Right? Which one has the fastest tangential linear velocity? What's the answer to that one? The one furthest from the center. Right? And in fact, its linear speed is just very simply proportional to its distance from the center. If it's twice as far away, I bet it's going to be going twice as fast in a linear sense, like meters per second, right? Because they all have the same angular velocity, okay, something like that, right? So here's for displacement, velocity, acceleration. To go from angular to linear, all you have to do is very simply multiply by r. And to go from linear back to angular, could you just divide by r? Right? Just go back and forth. You guys can do that, right? And finally, kinematic formulas. So here's with the units written. Here's the one just without the units written. So either one are similar type posters. Okay. We're going to be using all these today, by the way. Right, so right. Hey, these look like your linear type motion kinematic formulas, like x equals v naught t plus half at squared, and so on. Right? Except now it's for a turntable. How far is the turntable turned? How fast was it turning initially? How much time? Okay. If it's speeding up or slowing down its rotation, that could be alpha and radians per second squared, right? And okay, and they just follow suit with the others. Right. Guess that? All right. So there's a quick recap of a bunch of new concepts you guys saw yesterday. You guys have a lab page out. You guys have a turntable. It's about to be turntable time. You guys ready for this lab? You guys ready for this lab? Right. So I think I said before I hit record, we're not going to be able to finish the whole thing today, but we'll do as much as we can. You guys see name? You guys see name? Write your name. I'm going to write period 5, but you guys write your name. So when you turn this in, I will give you lab points. You guys ready? Ready? Okay. All right. Then, you probably have just a single mass slug that you can focus on. Maybe like, can you guys just pop that somewhere on the surface, right? And then this thing's going to rotate. You got to focus on that mass slug, like as if it's a single point. You guys got that? Something like that? Okay. Now, for me, I'm going to focus on this outside Roosevelt right here. Okay. But I'll leave the 3 Roosevelts on there so you can see a bigger context. But I'm going to focus on this outside guy. Now, you guys know, because we just talked about this, that the relationship between angular motion, it's spinning, and linear motion, like tangential motion, you just multiply by the radial size. So like this guy in the middle, he's not going anywhere. He's got 0 linear speed. Right? If I point a radar gun at him, he's getting dizzy, but that's about it. He's not actually moving anywhere. it used to be, right? So the further out you are, the further distance you go, like circumference around a circle, and the faster you go, like a radar gun speed. So I gotta know, where is this guy relative to the center? So let's call this guy at 0.0. This guy's at 7 centimeters out. This guy's at 14 centimeters out. You guys see 14 centimeters? Right. Now, how about your guys' mass slug? Just go ahead and pop it somewhere on the surface that's not right in the center. Right. You guys see it's so many centimeters from the center? Can you guys go ahead and measure that? Right. So I'm going to put that number in this box right here, where it says radius equals so many centimeters. You guys got that? Okay. Now my number is 14 centimeters. Yours doesn't have to be 14. It could be 9, 10, 11, 12, 13, 14, 15, somewhere in there, right? Right. You guys got how many centimeters from the center? You guys got that? All right. So the rest of this is going to play out like a two-part story. So here's what we're going to do. We're going to do 3 revolutions at constant angular velocity, or pretty close to constant angular velocity. Then I'm going to let it go. And it's going to, do you guys think there's some friction? It's going to slow it to a stop, right? Okay. So here, I'll demo that right here. So it's going to go kind of like this. You guys see how I have these Roosevelts oriented along the x-axis? I'll call that 0.0. That's a good convention. I'll go counterclockwise. That can be considered the positive direction. That's a common convention. Here we go. So we do, there's 1, 2, 3 revolutions. And then I take my hand off and it slows to a stop. Boom, just like that. You guys got that? Right, you guys see that? All right. So you guys got a stopwatch, right? Stopwatch. I'm going to clear out the stopwatch. Notice I set it back to 0. You guys got your stopwatch zeroed out? Right. Now, I'm just going to time the constant angular velocity part. You guys remember I did 3 revolutions? Right. But before I skip past this number, you guys see right here? It says theta equals 6 pi radians. Guys, where's 6 pi radians coming from? Why did I type in 6 pi? Because that's 3 revolutions, isn't it? Guys, 1 revolution is how many radians? 2 pi, kind of like circumference equals 2 pi r, right? Kind of follows that, right? Oh, so if you do 3 revolutions, that would be 3 times 2 pi. Oh, that's where the 6 pi radians is coming from. You guys that? Right. I wanted time. How much time does that take? Right. You guys ready? You guys ready? Right. So you guys do it. I'll do it. Okay. Here we go. If it's completely bad, I'll start over. But I might use this. Right. Yeah. Ready? So you guys got yours ready to go. I got mine ready to go. I'm just going to time the 3 revolutions, and then I'll stop it when the coins are back aligned right here. Okay. And go. 1, 2, 3, stop. And then okay, yeah, we'll go with that. Right. So yeah, okay, it's a little bit slow, but that's all right. My stopwatch is saying 5.56 seconds, and yours says whatever yours says. Okay. Maybe you did a little bit faster than me. Maybe you did a little bit slower than me. Okay. But I'm gonna go over to this time. I'm gonna write 5.56 seconds. Okay, and now, yeah, you guys don't write 5.56. You guys write whatever you got on your stopwatch. You guys got that? Okay. Now, one more thing. After I took my hand off, these Roosevelts kept on growing, right? Because the turntable kept on turning, and it didn't stop until it got right here. You see that? So I wonder, how far did these Roosevelts continue to roll? So here's my pen to mark where they started. That's like the start finish line. Is that it went all this extra angular displacement? You see that? And I see it's more than 180 degrees. Now maybe yours is more than 180, maybe not. Right? Maybe. Hey, did anybody have theirs go more than 360 degrees? Did anybody have that? Right? Maybe you did. Right? Mine went a little more than 180. I need an exact measure. Guys, what measuring tool can I use to measure this angle? A protractor. And so throw the protractor on the board. Oh no, my protractor only goes up to 180. That's okay. Mark off 180 and then zero out that point. Whoops, realign that. Zero out that point and then measure the extra part. And if yours went around more than 360, you can just add 360 to whatever angle. So it looks like an additional, trying to get this about right, about 30 degrees right there. That's, oh wow, that's really close to 30 degrees. I'll call it 30 degrees. Right. Now yours is whatever yours is. Okay. So guys, I have 180 plus 30. What is 180 degrees halfway around plus an additional 30 degrees? That looks like 210 degrees on mine. And yours is not going to be 210 degrees. Yours is going to be whatever yours is. Okay, you guys see that? Right. I'm going to skip down here to the second half of the story. See where it says release and allow to slow to a stop? Right. See theta stop? Right. Is, ooh, wait a minute. This says radians. Guys, can I write 210 degrees in this box right here? Should I do that? No, because it says radians. I need to convert that to radians. You guys see a margin in your paper down the bottom? Let's do a little math right here. Right, theta stop, subscript stop to tell you what theta you're talking about, equals, right? Now, mine was 210 degrees. That's why I'm writing 210 degrees right here. But you guys don't write 210. You guys write whatever you got on your own turntable, okay? You guys got your own stopping angle? You guys got? Right. You guys remember where I got 210 from? Here. So I did. Right. So relative to this pin, I'm looking for this big old wedge that is slowed to a stop. It was 180 plus 30. That's where I got the 210. Okay. Right. So you guys know where I got 210. You guys have a different number there. Okay. Let's convert that into radians. Convert. Unit conversion. It's the time to break out some railroad tracks right here. Is this a technique that pops up about every week in the class? Yeah, it's a pretty good one, isn't it? And you probably use this a bunch in chemistry, I think. At least that's where I learned this technique. Okay. Let's convert degrees into radians. Degrees into radians. Oh, I can think of a few different ways to do that. Guys, what's one way to convert from degrees into radians? Who knows one way to do it? How about this? 1 radian is about how many degrees? Did anybody remember? Like if you're looking on the protractor and I say mark out 1 radian, you make a wedge that's 1 radian. How many degrees is that equal to? Is it 57 point something? It's like 57.3, right? That's one way you can do it, right? How about this? Okay. Guys, 1 trip around the circle, 1 revolution is how many degrees? 360. How many radians is that? 2 pi, right? Like circumference equals 2 pi r, right? 2 pi. Right? And then my first period class, one of my students said, "Hey, I know conversion. I can just go halfway around the circle." Guys, halfway around the circle, how many degrees is that? 180. How many radians is that? Pi. Right? I'm going to use that one myself. I'm going to go. There's pi radians is equal to 180 degrees. I like to do that myself. Right? Ooh, guys, should the pi go on top or on bottom? The pi. Yeah, on top. We got pi so pi radians is equivalent to 180 of these degrees. It's the same thing. You guys got that? Okay. Oh, look what happens to your degrees. Goodbye. And now your unit left on the board is radians. So let's multiply across the top, divide across the bottom. So what's 210? Well, you don't have 210. You have whatever degrees on your paper. Okay. However many degrees, say times pi over 180. Or you can do times 2 pi over 360. Or you could do times 1 over 57. Tell you about the same thing. So I'm looking at 3.665. I'll call it 3.67. 3.67, and that would be radians. That's my stopping angle, my stopping angular displacement. That's that wedge that was just a little over half the circle. Okay? And that's going to go into this box right here. It says theta stop equals, I'm going to write right here, 3.67 radians. Okay. And you guys write whatever number on your paper. All right, all good so far? Right. You guys good? Of course, with your own numbers. Okay. All right. Okay. So I think at this point, we have enough information. We can fill out all these boxes. Okay. And that's about after we do that, that's about where the bell has been ringing today. So we're gonna have to save all the graphs for Friday probably, but I think we'll be able to get these boxes today, or at least most of them here. Okay. All right. So let's backtrack to the first part of the story because I wanted you guys to get the stopping angle, but we're going to go back and focus on the first half of the story, which we hadn't quite finished yet. All right, you guys ready to go to the first part of the story? Right. So this was where, you guys remember we were doing 3 revolutions. That was 6 pi radians. It took so many seconds. You guys remember all that? Pretty much a constant angular velocity. And what is that constant angular velocity? That's the next question. You guys see that's in radians per second? Guys, if I know how many radians and I know how many seconds, how do I get radians per second? Divide? Yeah. Yeah, divide radians by seconds. So in your calculator, now everybody can type 6 pi because everybody has 6 pi radians. It's 3 revolutions. Okay. Divide by however much time it took you to do those 3 revolutions. So for me, it was this many seconds. Can you guys do that many radians by that many seconds? All right, so I'm dividing. I'm getting this many radians per second. Put that right here. Boom, boom. Okay. All right, you guys got how many radians per second it was going at a constant angular velocity? You guys got that? Okay. Now, notice I put a subscript not on that because I'm saying at the moment that you let it go, it was probably spinning about that fast to begin slowing to a stop, which enters into the second half of the story. But here, roots, okay? Right. That's what the subscript is all about. All right. All right, you guys good? You guys good? Working out. Okay. All right. So now we have all the angular values for the constant angular velocity part of the story. I know it rotated this far and that much time, therefore it was rotating that fast at pretty much constant. Hey, I wonder what were the linear equivalents. So like that outside Roosevelt, if he was on a giant circular racetrack, like how far was he wheeling around that racetrack? Huh. Guys, how can I get this box right here? How far did that outside Roosevelt move? Or your mass lug? How far did it move? How can I get this box right here? How far did something go in centimeters? How can you figure that out based on your rotational information? How do you go from rotational information back to linear? Just very simply multiply by radius. Aha. Great. Guys, don't you know this number right here? Guys, what is this right here on your paper? 6 pi, right? Don't we all have 6 pi radians? 6 pi radians, right? Now, I have a 14 centimeter distance. Yours may or may not be that, okay? Right. Guys, just multiply your radial distance by the 6 pi radians. Let's do that right here. So I'm going to take 6 pi radians. Whoops. Right. 6 pi radians. Multiply by, now for me, it was 14 centimeters. For you, it may or may not be. Okay. And I'm going to get how far around. So I'm looking at 264 about centimeters. Okay. Okay. If you also use the 14 centimeter radius, then your numbers would match mine for that box. If you use a smaller radius, then it's probably a little bit smaller than that. Okay. All right, you guys good? All right. Finally, to round out this first half of the story with the constant angular velocity bit, okay. How about tangential velocity? Suppose you had a speed gate set up and the Roosevelt comes through, zoom, or your mass lug goes through, zoom. Or what if you point a radar gun at it, it swings around, zoom, right? How fast is it going? So it's tangential velocity. I might say it's instantaneous speed, right? Something, okay. I can think of 2 different ways to get this box. They're going to give you the same number. What is one way I could get this box right here? Huh? Oh, okay, yeah, yes, some kinematic, like something to do with these numbers up here. Should I multiply something, divide something? How can I get this linear speed? This would be, by the way, if you're driving in a car, going around a curve, your speedometer would be pointing at some value. So it's kind of like that, your speedometer reading. How can I get the speedometer reading? Here, here's one way. Here's linear speed, like tangential speed. Can I just do angular speed times the radial distance from the center? You can do that. There's one way right there. Right there. I'm going to do that on my calculator screen. So here's my angular speed. I had 3.39 radians per second. Now, you guys don't have 3.39 radians per second, but you have whatever's in this box. You guys got that? Right? Multiplied by, and I have a 14 centimeter radius. So put that in there. That gives me, put it all together, 47.5, I'll round it to, centimeters per second. Read that? Okay. Guess that? Now, of course, your number is different than mine, but you guys see how I got that, right? I just multiplied these two together right here. But wait a minute, I said there was a second way to also get the same number. Guys, centimeters per second. Can I just say how many centimeters did he go? Divided by how many seconds? Can I divide these two? Is that going to give me the same number? I wonder if it will. Let's put it to the test. Time to test some physics. Now, my Roosevelt rolled 264 centimeters in 5.56 seconds. I'm going to divide that out. Guys, when I hit enter, what number has to pop up on my calculator screen? Yep, it better be 47.5. Let's see if it is. See if it is. Oh, yeah. Oh, yeah. Look at that. It's 47.5. It's the same thing. You guys see we just got this number two different ways, and they're saying the same thing. Right? You guys good? It's working out for you guys too, right? All right. You guys ready to move on to the second half of the story? Right. Now, there are a couple things we know. We know it went to a stop, so I went ahead and gave you guys 0 radians per second final angular velocity. It went to a stop. And also, real fast before things got too jostled, we did grab this angle and we converted it to radians, so we know how far it went to come to a stop. So we know that so far, right? Right, we know that, right? There is enough information at this point you can figure out everything else, and I'll walk you guys through that. So, how about this? Do you guys think this is probably going to be something to do with these kinematic formulas? You guys think kinematic formula time? Right. So what do we know? What do we want to know? Do you guys know? The stopping angle in radians. That is this box, isn't it? So many radians to come to a stop. Right. Of course, your number is different than mine, but you did measure in degrees with a protractor and converted that into radians. So you have some number in this box, don't you? Isn't that this right here? So, okay, so we got theta, which could also be this theta down here. Got that. Oh, hey, guys, what is final angular velocity equal to? 0. 0 radians per second. Went to a stop. How about initial angular velocity? Guys, right when you let it go, was it spinning this fast right here? Whatever number you have in this box, angular velocity initial, right? Hey, that's 3 kinematic values. Okay, so I'd like to know 2 other things. I want to know what is time and what is angular acceleration. Now, there's a specific way we're going to have to do this. You guys see the first 2 kinematic formulas each have those 2 same unknown values. So I can't use either one of those in isolation. But I could use the third kinematic formula to solve for alpha. And then I could plug that into, well, how about the second one to solve for t? You guys see that? You guys see the roadmap we're going to do? Because guys, this bottom formula, we know everything except for alpha. Solve for alpha. Take that, plug it in here, solve for t. Boom, boom. You guys see that? Right, that's our roadmap. That's what we're about to do right here. All right, so here we go. Let's go. Final angular velocity squared equals initial angular velocity squared plus 2 alpha theta. That's how we're sort of. Oh, by the way, let me mention this recording. I think I'm going to use this recording for Google Classroom. If you were in one of my earlier classes, I did a different technique where I had you guys actually use the stopwatch. Now, side note, if you're in one of my earlier classes, if you use a stopwatch and you empirically grab this time value, we kind of run into a little bit conflicting data. The numbers kind of align, but different ways of going about it, you get slightly different numbers. So instead, I wanted to do this technique where we just do a calculation so that everything's 100% consistent. Okay. So we're going to calculate acceleration, angular acceleration, I should say. And from that, we'll calculate the stopping time instead of measuring it with a stopwatch, which is a little bit iffy anyway. All right. So I think this is a better technique. Right, so you guys know, eyes on the prize. We're solving for that alpha right there. So I should know everything else. Guys, what am I going to plug in right there? 0 radians per second, because it's going to a stop. Now that's being squared. 0 squared is still 0. Okay. How about initial angular velocity? Are you guys going to get that from right here? That's why I put the subscript not right here. Because, okay, so it was spinning this fast right when you let it go, assuming you kept it constant the whole way through and up until the end. So I'm going to plug in that here. Now, my number is this many radians per second, which is not the number on your paper. So guys, don't just copy mine unless you want it for extra notes and you're really fast writing. You've got 2 sets of things going on. Okay? But you have your own initial angular velocity, which is different than mine. And that comes from this box. Okay? Right, you guys know where these numbers are coming from? Okay, plus 2 times. Okay, I'm solving for alpha. What's the rate that it's slowing down, which is going to be a negative number. Okay? And then times, let's see, how far did it go to a stop? Oh, isn't that when we broke out a protractor and got so many degrees, convert that to radians, and that ended up in that box right there? You guys remember that? Right? So I got 210 degrees, convert it to 3.67 radians. And that goes right there. It took that far, which is more than half the circle, to come to a stop. So I'm going to put that right here. 3.67, that's radians. Okay. Right. So you guys have a setup that looks pretty much like that, just with a little bit different numbers, because you have your numbers, I have my numbers. Right. Okay, so let's do some algebra, solve for this alpha. Okay, so I'm going to subtract this over. So that's negative 3.39 rad per second, and that's all being squared over there, is equal to 2 times alpha we're solving for times 3.67 radians. So that could look like that. Okay. Then divide down the 2 in the number of radians. Boom, boom. So that's going to look like, well, how about like this? 9 rad per second. Square that. Divide by. Oops, as a curvy looking division sign. Okay, it's a little better. Okay. I got a 2 down here. I got so many radians that came to a stop down here. Okay. Now, in your calculator, make sure that this is all grouped in parentheses, otherwise you'll get the wrong number. And that's all equal to alpha. Now I have my alpha isolated. Okay. So last step, alpha equal, here, I'll put it on this side. Okay. Calculator time. So calculator. Okay, I got a negative, so I'll go ahead and throw the negative down on the board. Then punch the rest in the calculator. I got this many radians per second, square that. So initial angular velocity squared. Then divide by, okay, now guys, this next part's really, really important. Open up a parenthesis. Because right after you hit divide by, open up a parenthesis. Okay, you have to have that, otherwise you're going to get it wrong. Okay, you guys hit divide by parenthesis. Just got initial angular velocity squared, divide by open parenthesis. Then do 2 times the stopping angular displacement in radians. So for me, it's going to look like that. Okay. This model calculator automatically closes your parentheses for you. Not all do. So if you have a different model, go ahead and close it. All right, then hit enter, and there you go. Remember, it's a negative value. I got this many, and that's, guys, what's the unit? What's the unit for angular acceleration? Radians per second squared. Exactly. Oh, yeah. Radians per second squared. Right. Okay. Of course, your numbers are different than mine, but it shouldn't be crazy different. Now, mine has, my turntable spins pretty good. So if yours had somehow even less friction than mine, which is possible, maybe you had something closer to like -1 or -1.2 or something, radians per second squared. If you have a turntable that doesn't spin very well, has a lot of friction, maybe this number is closer to like -3, -4, -5 radians per second squared, possibly. Right? Okay. But that number is going to go right here. And I gave you the negative sign. Look at that. Because I said, well, slowing to a stop. I'll go ahead and emphasize that by just go ahead and giving you the negative sign already. Do you guys write that number into that box? You guys got that? So there's the rate that the turntable was slowing down to a stop. given, you know how fast it was going while you were rotating it, constant angular velocity, you let it go, it stopped naturally at some stopping angle. We put all that information together and figure out the rate that it was slowing down. Radians per second per passing second. Call that radians per second squared. Right, everybody good? You guys good? Right. Now, I still got to figure out the stopping time. Right. Again, if you're in one of my earlier classes, I had you guys get this empirically with the stopwatch, but I think a better way to get this is really to calculate it. So is it time for, here, see if you guys remember where we are on the roadmap. Which kinematic formula are we going to use now to solve for the stopping time? The second one, that T right there. Could you use the first one? Yeah, but you would run into what situation? Starts with the Q. Quadratic. Yeah. So let's not do it. Well, let's do the second one. Okay. That a little bit easier, you guys think? Of course, you would get the same answer anyway. Okay, but let's do final angular velocity equals initial angular velocity plus alpha times t. Okay. Now this time I want to solve for t. Let me do something a little fancy. Okay. I'm going to split my paper and solve this in terms of variables and then plugging the numbers in. So in terms of variables, I could go omega final equals omega initial plus alpha t, solve for, solve for t. Okay, scratch that. It's just alpha. It's just alpha right there. Okay. Or if I plug the numbers in, does it go to 0 rad per second equals, now it was going at, or my paper, it's this many rad per second initially. Okay. Plus, and we just got a value for alpha, and it says negative values that you popped in this box down here. That's rad per second squared, and then t. Okay. That's if you plug the numbers in. Now, in terms of variables, I can subtract over the omega naught, and then divide down the alpha. Right. Especially my AP students, I'm encouraging them to be able to solve in terms of variables because they need to have that skill. Right. I mean, it's a good skill to have in general. Right. Hey, couldn't this be like the master answer that's going to get everybody's paper correct? Right. Now you have like some general answer that could answer everything. Right? But you plug in the numbers first. It's okay. Subtract this over. Right, and then divide by this coefficient alpha. So see what I get. Right, I'm getting stopping time is equal to 2.16. Actually, yeah, that does look about right also. So even if I had guys empirically do that with a stopwatch, and say I had a second stopwatch and I timed it, that does look about right. It took about 2 seconds or so to slow to stop. Yeah. All right. And hopefully you're getting something that's kind of in that vicinity. If you have a lot, guys, if you have a lot of friction on your turntable, should you get something smaller than or greater than 2 seconds? If you had a lot of friction. Probably slow to stop faster, maybe like 1 second, 1.5 seconds, maybe, right? Because what if you had one with hardly any friction at all? Do you think you could spin for like 3, 4, 5 seconds, maybe? Probably makes sense, yeah. Right. All right. So let's go to stopping time. I'm going to write that number right here. I got a value. Did you guys also solve for your own stopping time? You guys got stopping time? Right. Yeah, it's probably similar order of magnitude as mine. Not the same number exactly, but probably pretty close to that. Okay. All right. Everybody good? All right. All right. All right. We're going to skip this average bit. I want to say that until after the graphs. So we're going to say that for later. Okay. Let's do stopping distance, like in a linear sense. So again, this is like if you're going around a racetrack, how far around? Here, let me show you guys. Give you guys a visual right here. So I had this turntable. Remember, I did 1, 2, 3, and then I let it go right here. And then from this point, it slowed down and stopped right about here-ish. Okay. So suppose I'm focused on this outside Roosevelt. That's 14 centimeters away. And I took a string and I wrapped that string around. I said, and then I pulled that string straight. I said, how long is that string? Isn't that exactly what this is going to tell us right here? You guys get that? Right? What's that linear distance? or odometer of a car, if you like that one. Okay, guys, how can you get a linear distance from an angular distance? How do you get that? Who remembers? How do you go from angular values to linear values? You have to multiply by something. What do you multiply by? Huh? Does anybody know? To go from angular displacement to linear distance, what do you multiply by? Radius, your radial distance. Okay. Do you guys remember maybe from about 5th grade, circumference equals 2 pi r? You guys remember that? Right. Now, that's a very specific version of this one. That's exactly one round trip around the circle. That's called one circumference. Right? But we're doing more generally, like any trip around. Mine ended up probably right about there. So my pen angle. I'm looking for this angle on my own turntable. Right? So I say, well, how far is that? If I don't want to do degrees, I want to do radians, but we found that already. If I multiply that by 14 centimeters, because mine was 14 centimeters out, that'll tell me exactly this distance in centimeters. I can do that. And you guys can do that for yours. Okay, you guys ready to do that? So let's do that right here. Exactly what we're about to do. So I'm going to take my 3.67 radians stopping angular displacement. Right? Take that, whatever number's in this box. I'm going to multiply that by my 14 centimeters radius. And that'll tell me, yeah, it's 51.4 centimeters. That looks about right. Right. That's a pretty good distance. Guys, suppose I have a string that's 51 centimeters long, and I stretch it out and put that next to a meter stick. How much of the meter stick is that as a fraction? Is that about half of the meter stick? 50 centimeters would be half the meter stick, wouldn't it? It's about half the meter stick. That's a pretty good distance. Ooh, right. Circles can sometimes be deceptive like that. You know, you say, oh, circumference, that can be, whoa, that's a really long circumference when you stretch it out like a string. All right, let's do, we're going to do one more box today because that's all I had time in my other classes. I know we've got a little extra time in this class. I think we've got till yeah. Okay. So this tangential acceleration. So this would be like if you're hitting the brake on a car. So you're driving a car around a big old circular racetrack, you're hitting the brake, you're thinking like in a tangential linear sense. What's the rate that I'm slowing down? Oh, and look at the unit here, centimeters per second squared, right? Makes sense? It's kind of what we've been talking about the last like 5 or 6 weeks, right? Okay. How can I get that from the rate that the turntable is slowing down, which is an angular acceleration? Because how do you go from an angular value to a linear value? You multiply by the radius. Radius. Isn't that what we just did? Here, I'll point it out on the poster. Right, because it's this one right here. It's this one right here. These all follow the same format. We go from angular to linear, just multiply by r, and we're looking at this one right here. What would it be? Right? You have alpha, you have r, multiply them together. You get a. Let's do that. So I got 1.57 radians per second squared. It's negative, but I threw in the negative sign for you guys because it's slowing down. It's all good. Got that. Okay. Multiply by this radial size right here. All right, that's going to tell me 21.98. I'll call that, well, maybe negative 22.0. It could be like that. Centimeters per second squared. Aha. So it's slowing down at that rate. There you go. All right. You guys good? Okay. All right. So like I said, my earlier classes, which are actually a little bit shorter than this class, this is about where the bell's been ringing. So I'm going to put the pause right here. But guys, think ahead a little bit. Look at these graphs. I got theta versus t, omega versus t, alpha versus t. Ooh, that sure does look a heck of a lot like these graphs over here. X versus t, b versus t, a versus t. So here's 3 linear graphs on the right. Here's 3 angular graphs on the left. We're going to have to put those graphs together a different day, probably on Friday. So you guys weather the hurricane well, and I'll see you guys on Friday.